Hello everyone, today I will explain my second homework from Computer Orgabization and Archutecture class. First of all, I want to explain the instruction which you see on the screen right now. Then I will explain my README and my code. In this homework, the instructor gave us 15 hexadecimal ARM assembly machine code instructions. At first, these values look like only hexadecimal numbers, but actually each line represents one real ARM instruction. So, this instructor gave us already the code, the program, but not in normal assembly language. The program was given in machine code form as hexadecimal dump, and my job is to reverse engineering this dump. That means I need to work backwards. I need to go from hexadecimal machine code, then binary fields, then ARM assembly instructions. I'm not creating any code from my own idea. I'm decoding the program that already exists in the given hexadecimal instructions, which you see on the screen. For each hexadecimal line, I need to find the matching ARM assembly instruction. For example, one line in the dump is E3A01000. This is 132-bit ARM instruction. To decode it, I first think of it as binary because ARM instruction formats are explained as 32 binary fields in the lecture notes. Each hexadecimal digit represents 4 binary bits, so one 8 hexadecimal instruction represents 32 bits. Then I split those 32 bits into ARM instruction fields. The lecture note explained that ARM instructions start with condition field and op field. The op field helps me to decide what type of instruction it is. If op field shows data processing, then I decode it as data processing. If it shows as memory, then I decode it as memory. If it shows branch, then I decode it as branch instruction. So in this homework, I use those same lecture notes. I look like at the condition field, the op field, the opcode or comment field, the register fields, and the immediate or offset field. After I decode all of those fields, I can write the correct assembly instruction. For example, for the first one, which I said E3A01000, the decoded assembly instruction is move R1/0. It means we assign 0 to R1. But how we know this? We know this because the binary fields show that the condition is always. The instruction is move, the destination register is R1, and the immediate value is 0. So I did not choose R1 or 0 or the move instruction by myself. The machine code contains the register field, and that field says that's R1 or that's something 0 or something, etc. This is very important in reverse engineering. I must follow what the hexadecimal instruction says. If I change the register, the program may still look like real assembly code, but it will not produce the same machine code. And this assignment requires an exact match with the given hexadecimal dump normally. After decoding the 15 instructions, I wrote the reconstructed assembly code in the file named homework2s, and then I tested it in simulator. And the testing step is very important because it proves that my reverse engineering is correct. And when I assembled my code in simulator, the generated hexadecimal machine code matched the instructor's original dump exactly. So this confirms that my assembly code is correct reconstruction of the given machine code. I will show the pictures which I get as a result, and I will show my code now. I will show my simple logic and my README. Now we are beginning to walk through of the README file, and in the first part I wrote like what assignment asked me to do, etc. I have already talked about it, and then proved that my code is correct. Before the writing final explanation, I tested my reconstructed assembly code in simulator. Actually, that part serves to proving that my code is correct, and I prove it with screenshots of the simulator. And when we click to these links, we see that we got the numbers here, and these numbers are exactly the same with the instructors. Like I will open the second source also here. Yeah, as you can see in these two pictures, our codes are the same with the instructor gave one. Like I paste my code to simulator and I got these results. Now I can continue reconstruct the assembly code part. At the end, I will explain simple logic of my code and my code itself, what this code does, etc. But first, I want to go with decoding method use. First of all, I want to ensure that I explained the main logic of the content, how it decoded, and some examples from the coding part. Then I will explain the logic of the code and etc. Like we decoded what and this decoded code doing what. But first of all, I think the most important part is the coding part. So I want to give height to decoding method use first of all. Okay, for this homework, I used a method from lecture notes, and the lecture explains that ARM 32 instructions are 32-bit instructions. That means every instruction is made of 32 bits. In the assignment, the instructions are given in hexadecimal form. Each hexadecimal digit represents 4 bits. So, one 8-digit hexadecimal instruction represents one full 32-bit ARM instructions. And like when we look here, these numbers, we see here we have 8 bits, and each of them represents 4 bits. I mean, here we see 8 digits, and each of them represents 4 bits, so it is 32 bits totally. The lecture also explained that we use main 3 formats for like ARM instructions: data processing instructions, memory instructions, and branch instructions. And when we decode an instruction, we first need to identify which format it uses. The lecture says all of these formats start with a condition field and op field. So my first step is always to look at the condition field and the op field. The condition field tells me when instruction runs. What is condition field? I mean, it plays where? It plays the first digit. First digit is condition field, and for example, here we use E and B. Condition code E means always. So if an instruction starts with E, it executes always. But we have here also B. What B means? B means less than. So if an instruction starts with B, it only executes when the previous comparison result was less than. And these are important for instructions like add LT and BLT, and they depend on the flags from previous subs instructions. Okay, so let's remember this first looking condition field, looking op field. Okay, if op field equals to 0, 0, so we decode it as data processing instruction. If it is 0, 1, we decode it as memory instruction. If it is 1, 0, we decode it as a branch instruction. And After I know the types of instruction, then I decode the remaining fields. For data processing instruction, I use fields like condition, op, function, rn, rd, and src2. Okay, we know for this format, we use for this format, which I said condition, op, function, rn, rd, and rc2. Okay, for example, condition code, we looked at op 00 for data processing instruction, function opcode information, rn first source register, rd destination register, r to c second source register or immediate value. For memory instructions, I use that format, and as I said, that's for data processing instructions. But for memory instructions, I use condition op, function, rn, r to rd, r to c again, and if it is 01, it is memory instruction. So first of all, we need to look up. Rn is base register here, rd is being loaded or stored, r to c is offset. For branch instructions, we use this format: condition, op, function, and IMM24. And op, as we said, it needs to be equal 10. L means 1 means BL, 0 means 0 means B. IMM24 is the signed branch offset relative to PC plus 8. Now when we come to detailed instruction by instruction decoding, I want to go deeply, then I will explain first to instruction and last to instruction as the example, because in the README file I wrote all of them in detailed way, and it's just walkthrough. In this section, I decode each hexadecimal instruction by following this as I said in the beginning video: hexadecimal instruction, binary instruction, RM fields, and assembly instruction. So each RM instruction is 32 bits, and all of them represent 4 bits, and so each 8-digit hexadecimal instruction represents one full 32-bit RM instruction, as I said before many times. For the processing instruction, I use this format, and for memory instruction this, and for branch instruction this. I explained all of them in 4 parts, so I not stay stuck on them. And here we have E, it means always, and B, and that means less than. Okay, when we come to instruction 1, we see E3A01000. When we convert to binary, we need to convert all of them to binary. Like, we know that E equals to 1110 in binary, like, and in A, B, C, D, E. If I'm not mistaken, that's 14. And when we come to 3, we represent 3 in binary, and as we know that's 3. Then we have A equals to 10, that's 10, and it's just real, like, here we have 0 means all zeros, here we have 1, 0001 represents 1, and all 3 zeros we represent them with all zeros. So when we come to the processing format, we see that condition equals to 1110, and it's E, and 00 is OP, I is 1, CMD is 1101, S is 0, RN is all zeros, RD is 1, and source 2 is all zeros. And we know that this binary means all, and it's always, so we know that E equals to always. And in opcode, we said that 00 means data processing instruction, so we have 00, and we know that data processing. And we have if I equals to 1, it means immediate values used. We have CMD, if our CMD equals to 1101, it means move. If S equals to 0, it means that flags are not updated. If RN equals to all zeros, not used for move. And if RD equals to 1, it means that we use register 1. And source 2 means if all zeros, immediate value is 0. So what's immediate value? Immediate value is 0, and our register is R1, and we have move as operation, and it means that we assign 0 to R1. So we do not update any flag, and etc. We just like make equal R1 to 0. And the command field is 1101, so operation is move. The destination register is 0001, so the destination register R1. The immediate value is 0, so value is 0, as I said. So therefore, this equals to that. It means that I did not choose R1 in the code by myself, or 0 by myself, etc. Okay, and when we come to instruction 2, we again see the same format, like E3A0200A. In the binary, we know again that E equals to 14, and it means that. 3 is that. A equals to 10, it means that. Here we have 0, it means that. Here we have true, it means that. 0, 0, again we have A, and A equals to 10, it means that. That's our binary format. And when we come to data processing format, we have condition, OP, I, CMD, S, RN, RD, and source 2 again. And when we decode it, again we know that if condition equals to E in binary, it means always. If it's 0, 0, it's data processing instruction. If it's 1, it's immediate value. CMD means 1101, and it means move. S, if S equals to zeros, flags are not updated. If RN equals to all zeros, not used for move. And R2, because that's R, and immediate value is 10, because that's equals to 10. And then we know that we assign 10 to R, like that's move instruction, destination register field is that, 2, register 2, and immediate value is 10. So our instruction, this means that. By the way, during the explanation of first 2 instruction, I see that I need to explain one part also, so I added that part to my README. What that part does, actually, I said that like 1101 equals to condition, 00 equals to op, 1 equals to I, but how I know they equals to this? I know that condition represents bits between 28 and 31, op represents bits between 27 and 26, and I represents bit 25. Actually, bits 24 and 21 represents CMD, bit 20 represents S, bits 19, 16 represents RN, bits 19, 12 represents RD, and bits 0 to 11 represents source 2, and these are the like separation of the bits for binary, like. And for the decoding, I mean, we separate bits like that, so I know that these bits shows condition, and these bits shows OP, these bits show I, etc. I don't say all of them by myself. Here we have rule, and since it had in the lecture, I didn't, like, I knew it by myself, and I didn't thought that I need to add it code explanation, but when I explained for the video, I thought that it could be good if I add it. So I add it, and I have here like that. As I said, I explained instruction 1, instruction 2. And all other goes in the same way. I don't think I need to explain all of them because it's that the walkthrough, but as I said, I will explain the last two instructions, also instruction 14 and 15. And here we have hex code again, and in the binary it seems like that. As I said, we have separation of bits, and with the separation of bits we know that these 4 bits equal to condition, and this op again it's E, it means always 0 0 data processing instruction. I 0 register operand is used, and CMD equals to subtraction. If it is 0 0 1 0, it means subtraction. S1 it means that flags are updated. Rn means here we have register 3, and RD it means we have destination register as destination register R5, and we have source 2, it means hex equals to R4. And when we convert it to assembly, we see it's subs R5 equals to R3 minus R4, and we said that flags are updated, and so it's normal that we use subs, not sub, but what subs with S, so our flag can be updated like that. In the 15 again we have same tip, but here we have branch format, and it's condition or PL and IM. Condition equals to E, it means always. Op equals to 101, it means branch instruction. L equals to 0, it means normal branch, not branch with link, and it means that negative branch offset. And in assembly it means speed crash. It's really different from others because in speed crash all of them others which I explained now, like the we update flag or not update flag, we have some operation, some assignment or subtraction, etc. But here it's really different in speed crash, and we know that this means E, so it's always, and the branch format shows its branch instruction, and it's normal branch, not BL, because L bit is 0, so it's normal B branch, not BL. Like that, the branch offset goes back to the crash label after that part, so it means that this equals to B crash. And as I said, here I explained all instruction in this way, all instruction, but it's just walkthrough, so I do not want to waste our time with explaining all of them, because now I will go to explanation of simple logic of code and code itself. Now we are going to code it. And until that part, we learned that we have hexadecimal code. We need to convert it to RM32 instructions, so we forgetting the code, and actually that's our code, how it seems all the result of this 15 instruction decoding. And now I will explain that code, and for doing it, first of all I want to show the roadmap, simple logic, then I will explain code itself. As you know, in this at the beginning we have four actually I can say our code has 3 main parts: start, loop, and crash. And in the first part, the program initializes some registers. As you can see, we say that R1 is 0, R2 is 10, R3 is 0, R4 is 5 from the hexadecimal terms, we can say that. And then we come to the loop. At the beginning, the important value is actually R2, R3, and R4, because R2 will be used as the value that gets added, R3 will work like a counter, R4 will work like the limit for the loop, and after this initialization program actually goes to loop part. In the loop part, important operation is R5 equals to R0 minus R4. This is done by the subtraction instruction in the assembly code. As I said, it ends with S because we need to update flags. The result is stored in R5, but the more important thing is that if we get negative, we will go to this loop. If we will not get negative, we will not go to this loop. So this part is so important for us. Okay, in this program, the flags are used to decide if R3 is less than R4 or not. And at the start, as you know from the initialization part, R3 equals to 0 and R4 equals to 5. And the program calculates 0 minus 5, and it equals 2 minus 5. It means that's negative, so we come that loop, and again we increase R0 by R2, we know R2 is 10, and we add 1 to R3, then we go back to the loop part, again we test that part, our result 1 minus 5 minus 4, and it means again R3 less than R4, and we come again here also, and we increase R0 by 10 again, and it will be equal to 20, and we add 1 also R3, and again we come here, we repeat that part for the 5 times. At the end, 5 minus 5 will be equal to 0, so it will not be 0, and if it's not 0, it means it's not negative, so we do not need to come here and increase R0 or R3, and our value of R0 will be 50, and our R3 is 5 from now on. And if we don't go inside the if, then we'll come inside the else part, and this is the crash part. And after that part, we'll go to the source part of the code. Okay, we come to the program crash part. The crash section starts by storing LR on the stack. LR is link register. And in the simple logic, I wrote SP equals to SP minus 4, memory SP equals to LR. This means that stack pointer most down by 4 bytes, then the value of LR is stored at the new stack address. LR, as I said, is link register, and the link register usually stores a return address after branch with link instruction. In this program, the instruction before the crash section is BL crash. BL means branch with link, so it jumps to the crash section and also stores a return address in LR. Then, inside the crash section, the program stores LR on the stack. After that, program sets some registers again, as you can see here. R4 equals to 15, R5 equals to 10, R6 equals to R5 plus R4, it means to 25, and R5 again equals to R3 minus R4. Okay, in that part when we say that R5 equals to R3 minus R4, this updates the flags because the actual assembly instruction is subtraction with S. But in this crash section, the flags don't help the program exit. The reason is that the next instruction is an unconditional branch. The last instruction says, go back to crash forever. And in assembly, this is B crash. B means branch. There is no condition here. So it always go back to the crash label. This creates an infinite loop. The crash section runs again and again. Every time it runs, it does this again. So this part again and again. So every time the loop repeats, the stack pointer moves down by 4 bytes again, and link register is stored on the stack again. There is no stop condition, there is no return instruction, there is no system call to the end to the program. Though the program keeps storing link register on the stack forever. Eventually, the stack can reach invalid memory. When the program tries to write to invalid memory, program crashes. So the main reason for the crash is not the first loop. First loop is controlled and it stops when like error 3 reaches to 5 because it's not negative anymore. The crash happens because of the second loop, and the second loop is the crash loop, and it's infinite. It keeps changing the stack pointer. So the full logic is like first we initialize registers, then we run a loop while R3 is less than R4. Third, when loop ends, we go to crash. Then inside the crash section, we store LR on the stack and branch back to the crash forever, and that's it. This is the main logic of our code. And now I will explain how I did it all of them on the code. And that's the coded version of our code. As I said at the beginning, we had 15 hexadecimal dump, and we decoded it and get the actual real code which instructor gave us. And now I will explain that code itself. And with this, after the start condition, we have some initialization part, and like we assign 0 to R1, we assign 10 to R2, we assign 0 to R3 and 5 to R4. I said how we get this 0, 10, 0, 5, etc. We got all of them from hexadecimal dump, and also this R1, R2, R3, R4, all of them were given in those hexadecimal dumps. And then we come to the loop. Like after the first four instruction, we call loop, and in the loop we have subtraction part. Our R5 equals to R3 minus R4, and because of that S, we know that we need to update flags. Then subtraction is 0 minus 5, and that's negative, so it means that R3 is less than R4, and then we have next instruction, add LT R0 equals to R0 minus 2. It means that if R3 less than R4, then R4 equals R0 equals to R0 plus R2. Again, if R3 less than R4, R3 equals to R3 plus 1. As I said, we know all of those from these hexadecimal dumps. And with this hexadecimal dump, we know that here we have back to branch loop. If it is R3 less than R4, still back to loop again. And if it's not, branch with link to crash part. We have BL part, that's crash. It means we will go to the crash part. BLT, I need to say that less than, LT is less than, B means branch. If branch is less than, so back to the loop. And at the end, as I said, BL branch with link, and it jumps to crash after that part. Maybe I talk a little bit mixed because I'm so tired. And okay, it stores return address in link register, and after the main loop finish, execution goes to the crash section, and the first instruction is str lr sp /-4 and etc. str means store register. Here you say str. str is a store register. This instruction stores link register into memory. SP is stack pointer. That part means the stack pointer moves down by 4 bytes. The exclamation mark means write back. So updated stack pointer is saved. In the simple form, instruction means stack pointer equals to stack pointer minus 4, and memory write stack pointer equals to link register. And this is similar to pushing link register onto the stack. Then we have next instruction. In the next instruction, we make R4 equal to 15 and R5 equals to 10. We make R6 equals to R5 plus R4, and we update R5 flag here. This R3 minus R4. Here we have update because here we have S. And okay, then we come to the crash part. In the crash part, first we see this instruction. What this instruction does. str means store register. This instruction stores link register into memory. sp is stack pointer, and this means down by 4 bytes, and this exclamation mark means write back. So updated stack pointer is saved. So in simple form, this instruction means stack pointer equals to stack pointer minus 4, and memory at stack pointer equals to link register. This is similar to pushing link register onto the stack. And then we have next instruction. We make equal to R4 fourth register to 15, fifth register to 10, and sixth register to R4 plus R5, and we update here R5 also because it's equals to R3 minus R4, and we have S here, so we know that we update condition flag. But in this crash section, those flags are not used to escape the loop. And then we have bcrash. This is an unconditional branch. It always jumps back to the crash label, and there is no condition here, so the crash section repeats forever. It means that line repeats forever, and each repeated time, it stores LR onto the stack again and again, and moves stack pointer down by 4 bytes again. And there is no return instruction, no stop instruction, no system call to end instruction, so it can move into invalid memory, and then program tries to store link register into invalid memory, the program crashes. So the code has two different loop behaviors, this loop and this loop. First loop does not cause crash because it ends when it reaches to 0, R5 reaches to 0, but here we don't have it, so that loop never stops because bcrash always branches back, and this is the main reason for the crash. Actually, that's all. That's all about my code and my README. Again, at the beginning of the README, we have what assignment asks, code proof, our code. I explained that, the coding methods, and detailed explanation of the coding, all instructions I have here. Then here I explained the code actually inside the my README file. Burada at that part, comparisons, branch, loops, etc. I have explanation of all of them in my README file, and here I have simple form logic and final summary. So you can check everything, like including code and simple logic form, from my README. You do not need to look that part actually, but if you want, you can look to prove images from here and here, code, logic from here, code from here, all of them true. Also, I wrote all of them into the README file. Thank you for your watching. Goodbye.